Right, welcome to watch the interview about the focus issue of JMR. My name is Tianyu Liu. I'm a postdoctoral associate at Virginia Tech here in the United States. And today our interview will about a JMR focus issue here, as like in my hand, entitled The Porous Carbon and Carbonaceous Materials for Energy Conversion and Storage. And this focus issue is the fifth focus issue of JMR as this year, and it was just released in May this year. And this issue collects 3 reviews articles along with 19 research articles. And it served as the, for me, or myself, I served as the lead guest editor of this issue, and other guest editors, including Professor Ya Li of University of California, Santa Cruz, in the United States, and Dr. Marcus Worsley of Lawrence Livermore National Lab, the United States, and Dr. Ten Zhai of Nanjing University of Science and Technology, China. And this issue covers a broad range of topics on the porous carbon materials for applications including batteries, supercapacitors, and heterogeneous catalysts. And joining me today are Dr. Raj and his graduate student from Penn State Du Bois of the United States, as well as Mr. Wang, a PhD candidate at the University of Wollongong of Australia. And both of them are authors of the papers collected in this issue. So first, I would like to welcome Mr. Wang and Dr. Raj for joining me this morning, and I guess for Mr. Wang, I would say good evening, and for Dr. Raj, I would say good morning there. And so let's begin with our interview by briefly introduce yourselves and about your research expertise. And let's begin with Mr. Wang, please.
Okay, thank you. I'm Zhijie Wang.
So for Mr. Wang, please introduce yourself to our audience and describe your research expertise.
Yeah, sure. I'm Zhijie Wang. I'm currently a PhD student at the University of Wollongong, Australia. I received a master's degree at the University of Science and Technology of China last year. And after that, I had a short period of employment as a research assistant at Tsinghua University, China. My research mainly focuses on advanced electrode materials for lithium batteries, such as carbon nanomaterials and two-dimensional materials. Besides, I also have an interest in developing high-performance cathode materials for potassium-ion batteries.
Okay. And how about you, Dr. Raj?
Hi, my name is Ram Rajagopalan. I'm an assistant professor at Penn State Du Bois. My research is focused on developing porous carbon materials for energy storage applications. In particular, I'm interested in developing different types of supercapacitors, basically based on carbon nanomaterials. We make high voltage EDLCs. We also make flexible solid-state supercapacitors and hybrid lithium-ion capacitors in our lab. And primarily, the research is focused on understanding what happens at the electrode-electrolyte interface, and how does the performance of the electrode-electrolyte interface determine the device properties, such as capacitance, energy density, power density, and cyclability of the device. And with me, I have my graduate student.
Hello everyone, my name is Amir. I'm from Penn State and I work with Dr. Ram Rajagopalan here at Penn State, and my bachelor is in chemistry and I have MS in inorganic chemistry, and I'm working in energy storage devices, same project, and my focus is mainly EDLC type, supercapacitors, as well as lithium-ion capacitors. So we are trying to improve the energy density, at the same time power density of these energy storage devices.
All right, thank you for both of you for introducing yourself and also your research expertise. And as I mentioned, both of you are authors of the papers that are collected in our focus issue. So I would like you to give us some brief introduction also on the main content of the paper that you published in this issue. So let's begin with Dr. Raj.
Well, the primary goal in this paper was to develop a porous carbon material that we could use for in high voltage ionic liquid based EDLCs. As you know, EDLCs have been there for a while, and the primary EDLCs were based on organic liquid or organic solvent based EDLCs, and mostly microporous carbons are used for this particular EDLC because the ion sizes that are used are much smaller than what you would see with ionic liquids. But when you go to ionic liquids, you have several advantages. First of all, ionic liquid is you can use it as a neat ionic liquid, so the concentration of the ions in the electrolyte are fairly high. It also, if we realize the potential, we can push both the capacitance and as well as the voltage of the device, because the oxidation potential of these liquids are fairly high. The drawback is that these are highly viscous. So now once you have a highly viscous and we engineer a carbon with a certain porosity for this particular application, it becomes challenging because due to the viscosity, it's hard to penetrate into the very small pores, which are called the micropores in the carbon. So with that in mind, basically we have designed in this paper carbon which has bimodal porosity. So there are pores there are both micropores that we large micropores in the range of 0.8 to 1.2 nanometers in these carbons, and also we have a fair distribution of a narrow mesopores in the order of about 4 to 8 nanometers. The mesopores act as the reservoirs and facilitate easy access of ions. So primarily the project is based on design of these carbons, and we also report the performance.
All right. Well, sounds good. And also, I just want to ask some follow-up questions as you to lay the background for our audience. Maybe some of them are not quite familiar with your research field. So you did talk about like supercapacitors. Can you give us some brief ideas about what a supercapacitor is, and is that something related to the batteries or what?
So in terms of construction, it is more or less similar to batteries. We have positive electrode, we have negative electrode, and electrolyte. So during charging, ions moves and pile up on the surface of activated carbon, and it forms like double layer sort of. It is basically electrostatic interaction between electrolyte and electrodes. During discharge, ions release to the solution again. So this is purely physical phenomena. There's no electrochemical reactions. That's why this device is considered as a high power device.
So it sounds more like it's kind of like another type of electrochemical energy storage device, right?
That's correct.
Okay, cool. Thank you. Okay, and I guess right now I just moved to Mr. Wang, and you published a review article about the hierarchically structured carbon materials for batteries application. So could you please share with us something about the main content of that paper?
Yeah, the title of this invited review is Hierarchically Structured Carbon Nanomaterials for Electrochemical Energy Storage Applications. And I finished this in review paper with Ms. Yan Wang and Dr. Xiaoliang Yu, and the corresponding author is Professor Yanbing He at Tsinghua University. As is known, structural hierarchy is ubiquitous in nature and quite important for optimizing the properties of functional materials. Carbon nanomaterials, owing to the unique and tunable physical and chemical properties, have been regarded as promising candidates for various energy storage systems. Constructing hierarchically structured carbon nanomaterials can boost electrochemical performance of nanocarbons. Therefore, hierarchically structured nanocarbons have attracted tremendous research attentions in recent years. In this review, we summarized the recent progress in hierarchical structured design of carbon nanomaterials and the potential applications in different energy storage devices. First, we give a brief introduction about carbon nanomaterials and the hierarchical structure advantages. Then, recent works on hierarchical structure design of carbon nanomaterials were summarized and classified according to applications in lithium batteries, sodium batteries, supercapacitors, and nickel-sulfur batteries. In addition, the challenges in hierarchically structured carbon nanomaterials in different applications were also concluded and reviewed. At last, design principles of hierarchically structured carbon nanomaterials were summarized and future development trends were prospected. We hope this review can appeal a broad audience and it will be helpful to the researchers that focus on this topic.
Thank you. And you mentioned multiple times, I think that's the phrase containing your title, that is hierarchical structure. And if I might miss it, but could you please explain again what the hierarchical structures are exactly referred to?
Okay, sure. Structure hierarchy is quite important in biological world. It shows complex architectures at a multi-length scale. In hierarchically structured materials, the structural elements themselves have structures. For carbon nanomaterials with hierarchical structure, they consist of primary carbon matrix structure and nanocarbon subunits. These subunits are always zero-dimensional carbon nanospheres and one-dimensional carbon nanofibers or nanotubes and two-dimensional carbon nanosheets. Such kind of nanocarbon subunits are grown on a fluorescent-sized carbon matrix or decorated on the surface in a specific manner to form a comprehensive structure. The most representative is three-dimensional graphene aerogel that constructed by two-dimensional graphene nanosheets.
Thank you. So if I understand correctly, that's more about it's a unique way of assembling of different materials with various sizes, dimensions, shapes, morphologies, and assemble them together and form a kind of like a composite materials with multi-functions, right?
Yeah, sure.
Cool. And also, I just want to elaborate on that part, since your paper is about batteries, and we know batteries are pretty indispensable right now for consumer electronics, particularly in the modern society. And for example, we use cell phones and we need batteries to power our cell phones. So compare with those commercial batteries or the materials that are used in the commercial batteries. What do you envision that the hierarchical structures can bring to the battery field?
Yeah, the hierarchical structure of carbon nanomaterials can elevate aggregation and stacking issue that reduce the active surface nodes of nanocarbon subunits. Moreover, hierarchically structured carbon nanomaterials also have interconnected porous network, which can facilitate the rapid diffusion of electronic ions, such as lithium ions. Therefore, the hierarchical structure enable taking full advantages of the unique properties of carbon nanomaterials. As a result, improved electrochemical performance, including specific capacity, rate capabilities of carbon nanomaterials can be achieved. In addition, the hierarchical structure of carbon nanomaterials is also able to load active materials such as tin oxides and silicon to increase the electric conductivity as well as serve as a buffer matrix. to the volume expansion during the battery cycling of the electron materials. Therefore, it can help to improve the battery performance of this kind of active material.
Thank you. So it sounds like the materials can actually elongate the lifetime of the batteries, so can make our potentially the cell phones works longer and becomes more robust.
Yeah, sure. Yeah.
That's a great idea. Thank you. And so I want to move to Dr. Raj. And for your paper, you talked about bimodal porous carbon materials for supercapacitors. And also I did some research about, again, the commercial supercapacitors. And the electron materials they use are mainly the activated carbon or a type of microporous materials, as you just mentioned. And also in some cases, they use graphene. So I guess you also talked about that in your previous answer, but I want you to maybe can briefly again summarize the advantages of the materials that you designed and published in your paper over those commercial materials that are currently being used in the commercial supercapacitors.
Yeah, with respect to bimodality, I think we can explain.
In terms of synthesis, we are using soft templating approach. So we are blending like two types of monomers, phosphor alcohol and fluoroglycanol. So during pyrolysis, phase separation happens. So we have two regions. One is mainly phosphor alcohol region, which provide us microporosity, and the other region is fluoroglycanol, which gives us mesoporosity. As Dr. Ram mentioned, having bimodality is really important for two main reasons, and one of them, it can allow us to utilize surface area effectively. And another like advantage of bimodality is we can improve the rate capability of the device, because these mesoporosity can act as a reservoirs and shorten the diffusion lengths.
Okay.
Now, with respect to the question on the activated carbons, yes, commercially activated carbons are used, especially coconut char carbons are the state-of-the-art EDLC carbons. But you have to understand that most of those carbons have been developed primarily with the organic solvents in mind. So the pore sizes of those things, those carbons, especially the coconut char, is fairly narrow. But that is hard to use in the case of ionic liquids. And the biomass-derived carbons like coconut chars are very hard to, it's very hard to create this bimodal porosity in a controlled manner. That's the big advantage with polymer-derived carbons, because here, depending upon the choice of the polymers, we could actually tune both the micropores and as well as the mesopores.
So your material both contain the micropores and mesopores, while the mesopores can help to facilitate the ion diffusion and improve the material utilization efficiency. So that gives higher charge storage capability, right?
That's right. And it's also the optimum pore size distribution, because you don't want too large a broader distribution of mesopores. When you have uncontrolled activation, then you get a broad distribution, which results in lower bulk density.
Okay. And so it sounds like a really a great discovery and a breakthrough in the technology. And the next question I want to ask you is, considering your materials, what do you think the challenges that should be addressed before your materials can be commercially feasible?
For commercialization, the key challenge, so in terms of actual processing, it's very similar to activated carbon. So the precursor is different. So we are using a different precursor. We are using polymerization. But the follow-up, which is the pyrolysis and activation, is exactly the same. And so it can be commercially integrated using the same process. However, the biggest challenge, as you know, with most of these energy storage materials would be the cost. With new materials, it will be the cost. So currently, the coconut char or the biomass-derived carbons are in the order of $15 to $25 per kilogram. So the challenge would be, how do you bring down that cost? And for that, the performance has to really stand out. So the dollar per farad would be an important number to look for.
Okay, thanks for sharing your insight. And so I guess we'll move to the last part. And I want each of you to give us, our audience, some remarks or any thoughts that you want to share with the materials research community about your research field. So I begin with Mr. Wang.
Okay, I would like to talk more about the main challenges and the future research trends on this topic. Despite the structure and the performance advantages of hierarchically structured carbon nanomaterials, the wide application in energy storage field are still hindered by several factors. First, the synthesis process of hierarchically structured carbon nanomaterials are still complex and costly. Developing simple synthesis procedures at a large scale and reducing the cost would be one of the future directions. Besides, there are several challenges for the various energy storage applications needed to be addressed. For lithium and sodium batteries, no initial Coulombic efficiency is a big challenge. Promoting stable SEI formation is important, and optimizing the value of surface area may decrease the decrease the capacity loss of carbon nanomaterials during the first cycle. For supercapacitors, the most important thing is to increase the type density and to increase the volumetric energy density of carbon nanomaterials so that they can be used in industrial applications. Constructing graphite aerogel may be a promising approach to achieve this goal. In addition, introducing some functional dopants such as nitrogen doping can increase the workability of carbon nanomaterials and thus improve the electrochemical performance. For lithium sulfur batteries, further increasing pore volume can increase the sulfur loading ability of carbon nanomaterials, and optimizing the ratio of micropores, mispores, and micropores have a significant meaning for promoting the electrochemical reaction of sulfur cathode. Functional group modifications on the framework of carbon nanomaterials can also effectively restrict the shuttle effect of polysulfide. We hope carbon nanomaterials can have wider use in the future.
All right, thank you. And how about Dr. Raj?
Yeah, over the last few years, you can see that the energy densities of electrochemical capacitors are steadily increasing due to new technological breakthroughs. And the breakthroughs are happening in terms of electrode designs, like the one that we mentioned, and different new electrolytes, and as well as in cell designs. And materials innovation is more or less the key driving force behind all these innovations. And the challenge is, as we keep coming up with new cells and new materials, it is important to realize that electrochemical capacitors are still a power device, traditional power device. So as we push the energy up, it is important to also maintain the high power and good cyclability that you get out of these devices.
Thank you. And so thank you both of you for joining me today and sharing with your research. And I want to say that what we shared today is only a tip of the iceberg about porous carbon materials for energy storage and conversion. So if you are interested in this kind of content, you can just refer to this focus journal, and there are more excellent works that talking about this type of this field of research. And for those of you, if you are interested in editing a focus journal for JMR, I have some, I would strongly encourage you to apply for a focus issue for this journal. So typically the JMR will send out the call for proposal at the beginning of a year. And so once you see that, you can try to identify the topic of the focus journal you want to organize, as well as to form an editorial team of your own. And you apply to this JMR editorial office. And once you get the approval notice, the JMR editorial office will reach you and set everything ready for you to move forward. So they are pretty helpful, actually, in helping me with editing this focus journal. So I would also sincerely thank the editorial office and also right now the video editing team for helping me with promoting this focus issue, and thank you for them. And of course, I want to thank for all the reviewers, the authors, and the two authors actually, Mr. Wang and Dr. Raj and his student in joining me today to share your opinions about these issues. And finally, I would also want to thank the audience and the readers of the focus issue. I hope you will find some really useful information for both of your interest, or if simply you want to expand your reading interest in this type of materials research field. And with that, I want to conclude this interview today, and thank you for joining us.